The primary challenge in moving quantum computing from the laboratory to a production-ready enterprise environment is not just a matter of physics, it is a matter of orchestration. As we transition into the era of utility-scale quantum computing, the bottleneck is no longer just qubit count, but the lack of a standardized framework for integrating these systems into existing software architectures. This is where Quantum DevOps emerges as the critical frontier. Quantum DevOps is the evolution of traditional continuous integration and continuous deployment, CI/CD, specifically designed for a world where applications must split their execution between classical CPUs and quantum processing units, QPUs. It is the bridge that allows a DevOps engineer to manage the lifecycle of a quantum classical hybrid application with the same rigor and automation applied to a standard web service. To understand the mechanical necessity of this field, we have to look at the unique friction points of quantum hardware. Unlike classical cloud instances that are essentially interchangeable, quantum hardware is highly heterogeneous. Every QPU has a unique noise profile, connectivity map, and error rate that can change based on daily calibrations. A quantum DevOps pipeline must therefore automate the characterization of the hardware before a job is even submitted. The pipeline doesn't just deploy code. It dynamically recompiles and optimizes quantum circuits based on the real-time health of the target processor. This involves automated benchmarking, noise-aware transpilation, and the selection of the best fit qubit layout for a specific algorithm. This level of automation ensures that quantum resources are not wasted on low-fidelity executions, maximizing the return on investment for expensive hardware time. A core component of this strategy is the shift toward hybrid microservices. In a quantum DevOps model, we containerize classical logic, such as data preprocessing, variational optimization loops, and error mitigation algorithms, while establishing a persistent, low-latency bridge to the quantum backend. This requires a rethink of container orchestration. We are moving toward a reality where Kubernetes manifests don't just provision pods on a cluster, they manage the quantum classical interconnect. The pipeline must handle the synchronization between the classical side of the loop, often running in the standard cloud region, and the quantum hardware, which might be located in a specialized cryogenic facility. Automating this handover is the only way to scale these applications beyond one-off experiments. Infrastructure as code, IAC, is also being fundamentally redefined. In a standard environment, IAC scripts define servers, databases, and networking. In a quantum DevOps environment, IAC must define quantum execution environments. This includes specifying the required coherence times, gate fidelities, and error correction protocols necessary for a workload. We are building systems where the infrastructure is smart enough to realize that a specific cryptographic task requires an ion trap system for high fidelity, while a sampling task might be better suited for a superconducting qubit array. By codifying these requirements, we remove the human-in-the-loop bottleneck, allowing for the rapid iteration and scaling that has defined the modern software era. Deeply and honestly, we must acknowledge that Quantum DevOps is currently in its assembly language phase. We are still building the tools that will eventually become the industry standards. But the goal is clear: quantum agnosticism. We are aiming for a world where a developer can push a commit to a repository, and the automated pipeline handles everything from the circuit optimization to the hardware allocation and the classical quantum telemetry. This is the missing link that will turn quantum computing from a research interest into a scalable commercial reality. By applying the principles of DevOps, automation, monitoring, and iterative improvement to the quantum stack, we are creating the operational backbone for the next century of computation. This is not just about better code, it is about building the factory that produces the quantum future. Beyond the technical orchestration, we must consider the security and compliance aspects of the quantum DevOps lifecycle. As quantum systems become capable of breaking classical encryption, the pipelines themselves must be hardened against quantum threats. This means implementing post-quantum cryptographic (PQC) signatures for every container image and every code commit. A quantum DevOps professional is essentially a guardian of the quantum supply chain. We must ensure that the instructions sent to the QPU have not been tampered with and that the data coming back is verified for integrity. This requires a new level of observability. Standard monitoring tools like Prometheus and Grafana are being adapted to track quantum telemetry, metrics such as T1 and T2 coherence times, gate error rates, and readout fidelity in real time. If a QPU's performance dips below a certain threshold, the DevOps pipeline must automatically fail over to a different machine or scale up error mitigation protocols. The role of simulation in the CI/CD pipeline is another critical pillar. Before any code touches real quantum hardware, it must pass through a multi-stage simulation environment. This includes functional simulators that verify the logic and noisy simulators that predict how the code will behave under real-world physical constraints. The Quantum DevOps pipeline automates this testing, providing developers with a quantum unit test suite. This dramatically reduces the cost of development as developers can catch errors in the simulation phase before committing to expensive hardware runs. This shift-left approach to quantum testing is what will allow large engineering teams to collaborate on quantum projects without stepping on each other's toes or bankrupting the project budget. Furthermore, we are seeing the rise of quantum-native version control. While Git works for code, it doesn't necessarily capture the state of a quantum system. We need tools that can version the calibration state of the hardware alongside the code. If a specific result was achieved on Tuesday, we need to know exactly how the QPU was tuned on that day to replicate the finding. Quantum DevOps is building the metadata layers that make scientific reproducibility possible in the quantum age. It is about creating a transparent, auditable trail from the high-level algorithm down to the microwave pulse sent into the dilution refrigerator. This level of detail is what will give enterprises the confidence to deploy quantum solutions for critical tasks in finance, drug discovery, and logistics. In conclusion, Quantum DevOps is the operational manifestation of the quantum revolution. It is the hard work of making the miraculous routine. We are taking the most complex machines ever built by humanity and wrapping them in the familiar, robust frameworks of modern software engineering. This is the path to the quantum internet and quantum cloud, a world where quantum advantage is a service that can be invoked with a single API call, backed by a pipeline that is silent, efficient, and absolutely reliable. The infrastructure of the future is being written today, and it is being written in the language of Quantum DevOps. We are not just managing bits or qubits, we are managing the future of information itself.